Good day, everybody. You're welcome to another edition of our chemistry tutorial class, simplifying chemistry to the best possible ways. So today we shall continue with our discussion on transition metals. So as you can see on the screen, our objective for today is to explain in details the chemical properties of transition elements. So in our last class, for those who actually did not watch the last one, you can actually take time to check the previous videos on the transition metals, as it's going to help in understanding the chemical properties of this transition metal. So today, our focus of discussion is to examine the chemical properties of transition metals. So transition elements are moderately reactive, unlike several other metals like the group 1 and group 2A metals. These are the S block metals. So the S block metals are generally reactive metals. So but transition metals specifically are special types of metals whose reactivity are very, very moderate. So we say they have moderate reactivity. And they are definitely different from the S block element and the P block element because electrons are only filled in the D orbitals, right? So electrons are filled in the valence D orbital. So this valence D orbital is the orbital in which the behavior, the chemical properties of these elements get their reactivities from. So one of the determinants of these chemical properties varies such that they have partially filled D or F block orbitals. So the D orbitals are the transition metals, while the ones with electrons in the F orbitals are regarded as the inner transition elements. So also, transition metals generally undergoes variable oxidation state, so that's another beautiful chemical property. They have prolific tendency to form complexes and either complex ions or complex compounds, formation of colored compounds or ions, and finally catalytic activities or properties. So these are the aspects we actually want to examine in details today. Now, the very first property of transition metals, as we can see, is partially filled D or F orbitals. So transition metals generally used to have partially filled D orbitals. For example, transition elements exhibit this property in their neutral state or in their common oxidation state. We actually look at how to write the electronic configuration of elements in their neutral state and also in their common oxidation states. So with that, we get to realize that transition elements used to have partially filled electrons in their D orbitals or in their F orbitals. So these electrons with this kind of property, we call them transition elements. Now we're going to look at one or two and explaining also those elements that are not considered to be true transition elements. For example, when you take a look at an element like manganese with atomic number of 25 will have an atomic number of argon core, which is 18, with a 4s2 and a 3d5. So we are going to consider this manganese a transition metal because it has what? It has a partially filled D orbital, which is filled in the D orbital. Out of 10 electrons, which is fully filled, it has just 5 electrons. So this gives that element Mn25 being regarded as a transition metal. If you check other transition metals too, you get to realize that they used to have partially filled D orbitals. So if you take a look at, let's say, cobalt, CO, a few seconds. So cobalt, which is CO. So remember what's the atomic number of cobalt? We have science teaches verdict. Cobalt masters in Congo, that's 27. So that's 27. So cobalt will be argon core, 4s2, 3d7. So we can see the D orbital is also partially filled. So we also call that a transition metal. But note fully well here that there are some elements that are not regarded as true transition metals. So those elements not regarded as true transition metal will not have partially filled D orbitals. Either they have empty D orbitals or they have completely filled D orbitals. So let's look at a few examples. When you take a look at copper, for example. Now copper has an atomic number of 29. So the electronic configuration is argon core Ar, right? 4s1 and a 3d10. So what does that imply? Copper here is not going to be called a true transition metal because the D orbital is completely filled. And the condition for us to have a transition metal is that the valence D orbital should be partially filled. So this is completely filled. So we don't consider copper a true transition metal. So if you take a look at another element, for example, it could be in the neutral state, it could be in the common oxidation state, or it could also be in the neutral state. Let's take a look at zinc, for example, Zn2 plus also. So with atomic number of 30, this is losing 2 electrons. Normally zinc should be Ar, argon core with a 4s2, right, and a 3d10. But now this zinc is going to lose 2 electrons from this orbital. So as a result, the final electronic configuration becomes 4s0, 4s0 and a 3d10. So because it has completely filled the orbital to be this, then we do not consider Zn2 plus as a true transition metal. Let me give one final example here. So another example is Sc3 plus, right? So Sc3 plus atomic number of 21. So this is going to give us argon core. Normally scandium should be 4s2, and a 3d1. So it's going to lose one electron here and lose one, I mean 2 electrons here and 1 here. So in the end, so this becomes, right, 4s0 3d0. So what this implies is that scandium does not have any orbital in the 3d orbital, so it is empty. So this also implies that Sc3 plus is not a true transition metal. So this is how to actually identify those transition ions or transition elements that are not true transition components. So that is that about the first property of the transition metal, partially filled d or f orbitals. Number 2 is that transition metal used to form colored compounds or ions. So a number of transition metals have that tendency to form, color compounds. A very common one is copper. Copper ion Cu2 plus is prominently known to have a blue color. Right? You must have worked with Cu2 plus in the lab, possibly looking at these ions in the form of colors. So Cu2 plus always has a blue color. It's a transition metal having this property. If you take a look at another one like Fe, that's ion, Fe2 plus. Fe2 plus has a green color. Right? So why do we have all these colors exhibited by these transition metals? It is simply because of the transition of electrons from one orbital to another. So you can see here. Now at first, transition elements are frequently colored both in their solid states, you can see that, both in the solid state and in the aqueous solution. So this is because the transition metals undergoes electronic transition between the orbitals of the d or the f suborbitals. So there is what we call the d to d transition and the f to f transition. So you remember that we said that the d orbital, for example, used to have a number of suborbitals. The d orbitals has 5 suborbitals. So if you are to pick the suborbitals, for example, we are going to have it this way. So 5 suborbitals. So right. So each of these suborbitals used to have two electrons. Now they are all not of the same equal energy level in arrangement. So it's, I think, something like this. So there can be transition of electrons from one suborbital of the d to another suborbital of the d. So if you have transition of electrons from this energy level to this, so if the electron will want to move back to its initial position, there is going to be emission of photons, right? There will be emission of photons, that is light, and the emission of these photons will correspond to a particular wavelength, which will give us a color, and the color is what is going to be observed by the transition ions. So the main reason why we are having this formation of colors is because of the electronic transition of the electrons from one suborbital to the other suborbital. It could be d to d transition or f to f transition. So that's exactly what is being explained here as one of the major cause of these color changes in this transition metal. So you got to realize that the colors are associated with partially filled d orbital. This is only observed in those elements that has partially filled d orbitals, like the ones with, for example, from 3d1 to 3d9. So elements with empty d orbital, that means elements that do not have d electrons in their d orbitals at all, like 3d0, and those that have fully filled d orbitals like 3d10 will not undergo this series, right? Will not undergo this color change. That's why elements like scandium, Sc3+, right, will not have distinguished color. So this is going to be colorless, right? Element like Zn2+, ions like Zn2+ will also be what, colorless, because in the case of Sc3+, the d orbital is completely empty, so it has a 3d0. While in the case of Zn2+, the d orbital is completely filled, so that's a 3d10. So this is actually how to identify the reasons why some of these transition metal forms colored ions. So below we have some ions, transition ions with their respective colors. So here we have these ones that has been mentioned here, like scandium, Sc3+, Ti4+, and so on and so forth. These are all going to be colorless because they either have empty d orbital, so either they have 3d0 or they have what, 3d10. They are either empty or they are completely filled. So for those elements with this kind of transition, with this kind of electronic configuration in their d orbital, so they will be colorless. So other ones, for example, with 1 unpaired electrons in their electronic configuration, like titanium, Ti3+ will be purple, this will be blue, and so on and so forth. So we can see respective ions with their number of unpaired electrons, 2 here, 3, 4, 5, and also with their variable oxidation numbers and their color. So there's a need for you to study this, for every student to study this and actually understand how their color transition comes up to be. So number 3, the third property of these transition metals is prolific tendency to form complexes. So transition metals generally have the tendency or the ability to form complexes. So we talk about formation of complex ions or complex compounds. This is because they possess low-lying empty orbitals that can accommodate electron pairs from the donors or the ligands. So generally, when you look at formation of complex ions, right, you'll be talking about substances like tetramine, tetramine copper 2 ion, For example, this is an example of a complex ion. So tetramine copper 2 ion is drawn this way, Cu with 4 different amine group, NH3, 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 and NH3. So with a charge of 2 plus, like this. So it can be written as Cu with NH3, 4, with a charge of 2 plus. So this is called tetramine copper 2 ion. Now you can see all these ammonia attached are regarded as the ligand. So the NH3 here, NH3 here, NH3 and NH3. They are known as the ligand. Okay, so these ligands are popularly molecules or ions that have lone pair of electrons. So ammonia is one of them. So looking at the structure of ammonia, for example, is a ligand because it has lone pair of electrons. So you can see. So this is the structure of ammonia. This lone pair of electron makes it being called a ligand. So it can contribute the lone pair of electron to the empty orbital of the copper, of the transition element of copper. Because copper has some, empty p block and empty. It could have some empty p block, orbital, and also it can have some empty d block orbital. So for these empty orbitals to be filled up, it's definitely going to be filled up by these ligands. So ammonia is not the only ligand that we have. We can have water. Water can also serve as a common ligand because water is a Lewis base. It also has electron, lone pair of electron. In fact, 2 lone pairs of electron. So this is water. Cyanide is another example. In fact, fluoride ion is also another example. So you have a number of ligands like that attach themselves to transition metals to form complex ions. So we can see that in this example. Another common example we see in the formation of these transition metals or complex ions, the very common example is hexacyanophthalate ion. So that is the FeCN6, then hexacyanophthalate ion. So this is called the hexacyanophthalate ion. To draw this, you'll be having something like this. See? Right? So it is Cn, 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 Cn. So then 3 negative. Now, what this simply implies is that the ligands here is the cyanide ion. The ligands are the cyanide ion. So they are the one contributing their electrons, right, to the empty orbital of the Fe. So leading to the formation of these complex ions. This is a popular behavior, a popular property of transition metals. So they can accommodate the electrons from the ligands to form transition complexes, to form complex ions or complex compounds. So note fully well that the number of ligands help us detect what is going to be the coordination number. For example, the example I gave at first, which is a tetramine copper 2 ion, that's Cu, right, NH3 with a charge of 2 plus. So here we have 4 ligands attached to this transition metal of copper. So we say the coordination number of copper is 4. And as for this, we are going to say the coordination number of this hexacyanophthalate is what, 6. So this copper tetramine, since it is having 4 ligands attached, so the shape can possibly be, it can be tetrahedra, right, or it could be square planar, right. But the main shape of this is what, square planar. So looking at this with 6 coordination number, this is going to be octahedra. So 6 coordination number is octahedra, 4 coordination number is tetrahedra or square planar. We can have 3 coordination number too. As for 3 coordination number, that's going to be trigonal planar, right. So we have either it is trigonal planar or what, trigonal pyramidal. So trigonal planar or trigonal pyramidal. So we also have other ones, but the scope of this discussion will not permit us to discuss it. Now, in addition to what has been said, complex ions or compounds consist of central metals, atoms or ions, to which several other ions or atoms or molecules called ligand are bonded, which is what I've just explained. The bonding between the central metal ion and a ligand may be either electrovalent or coordinate. So this is, the interaction could be electrovalent or coordinate whenever it's forming a compound. So the two important features of a complex ion or compound includes: 1, the net charge on the complex charge. This is the result of the charge distribution from the ligand and from the central particle. So what are we saying? We are saying that if possibly we are having, let's say Cu, right, with H2O and the 4 here, right, so and the 2 here. This is tetra copper 2 ion. As for this now, this is known as the net charge on the complex, the Cu2+, and it is being determined by the central atom of the transition metal. So this central atom or this central transition metal determines what's going to be the net charge. And then also the coordination number, which I've just explained, indicate the number of ligands grouped around the central atom. So that's an explanation for the third property of the transition metal, being having a prolific tendency to form complexes, either complex ions or complex compounds. So here, in addition, so just giving us examples of these complexes. So like neutral complex species, so we have NiCO4, right? We have AgNH32+. This is cationic because of the presence of these charges, the plus charge, right? So we can also have NH342+, and so on and so forth. Now, the presence of this square bracket is always an indication to show that, yes, these substances are complexes. So you can see square brackets, square brackets, square brackets. So it shows that they are what? They are complexes. They are complexes. This is anionic complexes, this is cationic complexes. But most often when they form neutral compound, then the complexes, the square bracket might leave the structures. So for some cases you can also see them. So that's all about that. Then the fourth one is the variable oxidation state. So transition element shows formidable multiplicity of oxidation state because the NX and N1D suborbitals of their atoms have similar or about the same energy level. So what are we talking about here? The reason why transition metals can have variable oxidation state is just because of the closeness between the 4s orbital and the 3d orbital. You are going to see some of these transition metals having more than one oxidation state. For example, Fe ion. Fe can exist as 2+, and you can also see it as what? Fe3+, right? So we can have manganese existing as a 2+, right? Manganese can exist as 4+, manganese can exist as 5+. In fact, it can exist as 7+. You get the point? So different, these transition metals used to have different, variable oxidation state, and we want to explain why do they have this variable oxidation state. Now, the primary reason why they have variable oxidation state is because electron can get transited, or electron can get removed from either the 4s orbital or the 3d orbital, because both orbitals have very close energy levels. So electron can be removed from the d, and it can also be removed from the s. So when there is removal from these, it can therefore lead to what? Formation of variable oxidation state. Hence, the electron in both sub-level are available for bond formations and may participate in bonding. So that's the primary reason why they can form this. Now, let me give us one practical example with the transition, with the electronic configuration. That will guide us on what we are actually talking about. So if you take a look at Fe26, so we can have Fe2+. So this is going to give us argon core Ar with 4s2 and a 3d6. But when electron is to remove, it can be removed from this 4s orbital. So that will be 4s0. So this is going to be the oxidation state of this Fe2+. So, but if it is for Fe3+, electron can definitely be removed from the d orbital. So it's going to be like this, 4s0 and a 3d5. So the ability for electrons to be removed either from the 4s orbital or the 3d orbital is what makes them exhibit variable oxidation state, and then they lose this electron and they can form bonds with other elements or ions. So we can see that, just like I said, in a Cu, we can see the Cu here is existing as a Cu+, losing one electron and then giving us this. So it's also possible that it loses 2 electrons and giving us 3d9. So there could be variable ways by which electrons could be lost, and so that tells us about the behavior of this orbital. In this case now, for example, Cu+, the electrons was removed from the 4s orbital, 4s1 orbital, while in the Cu2+, it was removed from both the 4s orbital and the the 3d orbital. So that's how to analyze and detect which one is going to be most appropriate, and then giving the description of their variable oxidation state. Lastly is catalytic activity or ability of this transition metal. Transition elements generally used to have catalytic properties, so that's why you can see that in most of these chemical reactions in chemistry, when you make use of catalysts, those catalysts are often made up of transition metals or transition elements. So we are going to see the primary reason why they do that. Now, transition elements, both in the elemental form and in their compound form, are effective and important catalysts. A catalyst is a substance. This is just a simple definition of a catalyst, just as a form of remembrance. So a catalyst is a substance which alters the rate of a chemical reaction without itself undergoing any permanent change. So that's a catalyst. So transition elements exhibit this property because, now this is a primary reason why they exhibit this property, because they can easily lose or gain electrons. So they undergo redox reaction. So they can easily lose electron and also gain electron without themselves undergoing any reaction in the process. They do not interfere in the reaction in the process. So for example, you have a number of chemical reactions with this catalytic property. Now, we are going to list some reactions and then tell us the catalysts that are actually applicable. In his, we have ammonia, that the catalyst used in Haber process. What is Haber process? Haber process is the industrial preparation of ammonia. So that's NH3. So the catalyst often used there is finely divided ion. You can see finely divided ion. Ion is a transition metal, so it does have this property that is explained, that is the ability to easily lose and gain electrons. Another one is a contact process, right? Contact process. So contact process is the manufacturing, the industrial preparation of H2SO4, that's sulfuric acid. So the catalyst often used here is vanadium 5 oxide, V2O5. So you can see the vanadium here is actually a transition metal. And in several other reactions like hydrogenation of oil, that is the production of fats and butter, the production of butter and margarine, also that is hydrogenation of oil, right? So hydrogenation of oil, what do you use? You use platinum, use palladium, or use nickel. So platinum, palladium, or nickel are all transition metals. So in some other reaction also, like the decomposition of hydrogen peroxide, H2O2, right, to give us H2O and oxygen. This is one of the ways by which you can prepare oxygen in the lab. So laboratory preparation of oxygen. The catalyst used there is manganese oxide, MnO2. So which is also an example of, magnesium here is an example of a transition metal. So you can see here how important these transition metals are in the catalytic process. So this is actually the 5 major chemical properties of this transition metal. So today we have been able to discuss the major chemical properties of the transition metal, and I hope you understand the conception. In our next class, we shall be examining some of these important transition metals, how they are extracted, some of their compounds, their uses, and their properties. Have a nice day. Bye for now.